The first presentation for today is from Christopher Kunz, and he's talking about software-defined networking in an open source compute cloud. Have fun.
Good morning, everyone. I hope everyone's all right and didn't get to bed too late last night. I actually tried to shovel in a couple other slides about what transpired on Tuesday, and I'll just talk about this real quick because it's the actual bug is a real good example about how stacked idiocy can lead to catastrophic problems. On Tuesday, we all learned about a new bug in OpenSSL, which has impact on about 1/4 of all SSL-secured web servers. And I thought it would be good to have some up-to-date information and a little more in-depth detail than what you see on the typical Slashdot style articles. First of all, I'd like to introduce myself. My name's Christopher. I studied computer science in Hanover, Germany, and did my PhD there in 2011, actually, not 12. Ironically, I had an SSL-related topic, and I actually worked with the OpenSSL API for a while, so I know the pain that people are probably going through right now. I've been working for a hosting company called Filou for 15 years now. I have some admin experience, therefore. I couldn't help it. And I used to do a lot of PHP back then, and I'm not really shy to admit that because it has its merits. I wrote a book about PHP security, which is a very grateful topic because there's a lot of stuff to write about. And in my free time, I mesh steel into people. That's a bit odd maybe for some, but it's really fun. Just a very quick ad about my company. We are a hosting company. We offer everything from colocation racks in Frankfurt, Germany, to IaaS solutions. We have written something that's between a toolkit and a middleware for our own cloud product, which is completely based on open source software. We use QEMU, KVM for virtualization, and Open vSwitch for the network layer, and we have a Ceph cluster as a backend storage. We are a 100% subsidiary of Thomas Krenner AG, the hardware vendor, who is also sponsoring the conference, and I encourage you to visit their booth and look at the machines that they have. These are the machines that run our cloud. So, Heartbleed in a nutshell. It has a very cute name. I think it's one of the few security problems that has an actual logo, which is very impressive. And it's not a very cute bug. It's a pre-auth, pre-logging universal OpenSSL bug for OpenSSL 101A through F. And it was introduced very early, actually, in 2012. So it's been present for OpenSSL since sometime in 2012. It was committed to the source code repository in I think New Year's Eve 2011. It allows remote attackers without authentication or any other preconditions to make a 64 kilobyte memory dump of the service memory. Wait a second. Yeah, that's a remote memory dump, and you can basically read from the service memory in chunks of 64 kilobytes, and of course you can repeat the exploit as often as you want, so you can read a lot of memory if you need to. This memory dump may contain, and I've seen most of these already, stuff like URLs, HTTP headers, random stuff. I've seen PHP source code and Perl source code from scripts that were running on the web server fly by me. And it's also possible that SSL certificate private keys are contained in that memory dump. So before I go a little more in detail about the actual hole and what happened and what we're going to do to fix it, what's actually being done there that was vulnerable. Sometime in 2011, a PhD student at the University of Applied Sciences in Münster, Germany, was working on his PhD project, and he was working on ways to make datagram-based protocols more reliable and encrypting datagram-based protocols. Basically, what he was trying to do was to introduce some kind of session mechanism on UDP-based encrypted connections, if you will. For that, he introduced a Heartbeat extension to TLS over UDP or datagram protocols, which is DTLS. And he did it the proper way. So he had an ITF draft, he did an RFC, and he also did some code and committed that to OpenSSL. And it was committed and pretty quickly acknowledged by Stephen Hansen sometime around 15th till 31st of December 2011. And basically that's when the problem came to pass. The problem that we are seeing is not really a crypto bug. So it's unrelated to Beast or other holes that we've seen in the last years, which are now mostly attributed to the NSA planting backdoors somewhere. The cryptographic functions of OpenSSL are not affected, at least not their primary function. If you leak a private key, your crypto is still broken, but this is not the primary problem in the bug. It's also not a completely arbitrary memory disclosure, so you can't, I don't know, dump kernel memory or something. You can only dump what belongs to the process that is being exploited, web server, IMAP server, something like that. And it's not a remote root hole. You will be very hard pressed to find, I don't know, root passwords or SSH keys or something in that memory dump, so you will probably not be able to root a server with that, we hope. That's why it has a relatively low ZVE score of 5, because the higher scores are mostly reserved for code execution bugs. So what happened here? What happened was that the guy who did his PhD thesis designed a protocol. And he designed a heartbeat protocol that he wanted to be very flexible. So what he did basically was he had a heartbeat packet and a response packet. And the response packet was supposed to be identical to the heartbeat packet. So if I say hello to you, you say hello back. And if I say foobar, you say foobar back. What he also thought to be a good idea was that the client actually would have to tell the server how long the packet is, the heartbeat packet, instead of the server just looking at the packet and the payload and just taking its length. So we have a 16-bit payload length parameter, and we have a payload. And both are user supplied, and the payload can be arbitrary content. That's actually a quote from the RFC. So we have arbitrary content sent from the client to the server, and the client can also tell the server how long it is. Nothing can go wrong, right? Of course, something can go wrong, and you can see that here. We have a memory allocation here, and then we have a memory copy. And the BP is the buffer that was defined, initialized 2 lines earlier, and PL is the payload length, and payload is the actual payload. So the latter 2 variables are completely user-defined or client-defined. And what happens is that we allocate payload plus 19 for padding and overhead bytes of memory. And we copy PL bytes of the payload via memcopy to construct the response. Actually, what he was trying to do was basically copy the payload one by one to the response packet to have identical payload and response request and response payloads. So what happens is that the client sets the payload length to 64K and only sends 1 byte of actual payload in the heartbeat packet. And that what happens now is that the memcopy still copies 64 kilobytes of memory, but only 1 byte of these is actual heartbeat payload, and the rest is memory from the surrounding process. So this is what went wrong, and this is what happens if you test the vulnerability. There's a couple of web scripts to run. There's lots of Python proof of concept scripts, and there's probably also a Metasploit package or a Metasploit module right now. One of the more popular scripts is one that you can download from GitHub, and it can test any TLS-enabled TCP service, no UDP yet. It also has support for StarTLS, so if you have StarTLS FTP or SMTP services, you can test that too. It conveniently dumps the full 64K of memory for you if you test and the server you're testing is actually vulnerable. And this looks like, this is one of these moments where alt tabbing doesn't work. Yeah. This looks like this. I basically obscured the host a bit to protect the innocent, but I actually found a couple ones that are still vulnerable. And what happens here is that the script starts in a TLS session and sends a heartbeat request with the values that I just talked about. And what comes back is basically memory dump. This is a full HTTP header. It's probably a type of 3 installation. So this is the user cookie for the type of 3 front-end user. And there are Google things here, and there's a PHP session ID here. So basically, if whatever happened in this request that's being dumped here was done by an authenticated user, I could just go ahead and steal their session. So that's not really good, because in my tests that I did yesterday and the day before, I also saw, I don't know, whatever you transmit over the web. I saw contact forms, private information for customers, stuff like that just flies by you in clear text, because obviously memory contents cannot be encrypted. So it's pretty catastrophic. This is one of the screenshots that circulated on Twitter, where people actually exploited Yahoo, and that's Yahoo Mail. You can see in the lower 3 lines that someone was logging in with the username Agnes Sadhu Boateng, and the password is obscured. So Yahoo had a real issue with passwords, and we have announcement by a couple of cloud, SaaS, and whatever services to immediately change passwords, and I don't think that's uncalled for. So if you dump memory here, what you see is not deterministic. So right now, I think the opinion is that you cannot calculate what kind of memory you get in return. So you cannot force the server to dump its certificates or private keys and stuff like that. Most of the stuff is boring. It's just garbage. Or sometimes I saw GPL licenses fly by, so basically from some kind of script headers, I guess. You can just put up an endless loop and dump stuff there and put it into an out file. People are not going to see what you're doing because it's pre-logging, so you don't see anything on the web server logs. The only thing to detect right now is have an IDS that has signatures already. I guess there's probably going to be Snort signatures soon, if not already. I know that Juniper already updated IDS signatures, so you can detect this, of course, if you look into the TCP packets. Affected services are, above all, SSL-enabled web servers that run OpenSSL 101A through F, but also mail servers, IMAP over SSL, POP3, if anybody still uses that, SMTP, SMTP via start TLS is also vulnerable as long as the vulnerable OpenSSL libraries are used. OpenVPN is maybe vulnerable. People weren't sure yet. They released new versions also for the commercial OpenVPN product yesterday. Maybe other VPN products, probably Cisco is vulnerable. IRC has a problem, IRC over SSL, XMPP, FTP over TLS is also potentially vulnerable. There's also a vulnerability in Android 4.1.1 because that's the only Android version that ships OpenSSL with the right version and also with a heartbeat function enabled. OpenSSH is not vulnerable. It uses OpenSSL code, but only for crypto, not for session establishment and session management. So OpenSSH doesn't have a problem, which is good because I don't want to know what you would see in an OpenSSH memory dump. For Linux, only relatively new versions are affected, or for Debian at least. I run a lot of Squeeze, so I didn't have that huge a problem. Many of my customers are still on Squeeze, so that's still OpenSSL 098F, I think. But Debian, Wheezy, Jessie, and Sid are affected, and there are fixes for Wheezy and Sid, or were at the time of writing. That was Tuesday evening. Ubuntu is affected. Red Hat Enterprise Linux 6 had a patch. I don't know if they have updated packages by now. And everything else that ships OpenSSL, and that's pretty much probably everyone, because I don't know if a lot of people use new TLS or other SSL TLS libraries, but I don't think there's very many. Clients are also vulnerable, and I think we're going to see a lot of client-side stuff in the next weeks, because that's something that's often overlooked. If I run a server that's crafted to send these crafted heartbeat packages, I can exploit clients, so I can get memory dumps from clients. We don't really know what a memory dump from a Firefox would contain. I'm not sure if it's at all interesting, but if it is, we can see funny things probably. Other affected stuff, Cisco stuff. They say they don't generally use OpenSSL, but their SSL VPN products are probably affected. Juniper has released fixes for their SSL VPN product. They don't have any yet for the SSL-based management interfaces for their routers or switches or infrastructure stuff. We don't really know about stuff like Big IP or camp load balancers. We don't know if AVMs, Fritzboxes are affected, and we have another hole in the web administration front end again. Maybe your home NAS is affected, QNAP or Synology. They all ship basically Linux-based, Apache-based SSL secured web service with their products. There's a vendor list on the CERT homepage where you can check out if your product is affected. There were still a lot of unknowns at the time I looked at it last time, yesterday, but I expect it to fill up pretty soon. So what are we going to do against this? Yeah, it's really easy. Security Hulk says it's easy. Just revoke private keys and retract any data ever sent, and everything is fine and dandy. First of all, you have to upgrade to a fixed OpenSSL version, and don't just upgrade OpenSSL, you also have to upgrade the libSSL package on DEP-based systems. Then restart all services that link against the old library. That's really a big point. Some people have resorted to rebooting to fix this. Basically, it can happen that you have restarted Apache and you're still using the old library because the deleted version is still in the linker cache or something. I'm not very deep in Linux dynamic linking, but I've seen it happen. I've seen machines that had a clean new OpenSSL library, but were still running the old one on maybe Dovecot or any other SSL using service, and Apache was then still affected. So basically what you can do is you can use check restart, which is provided with the Debian goodies package, or you just use elseoff to see which processes still have a version of the deleted, that's the grep there, the deleted libSSL in use. If you use static binaries for your stuff, you will have to recompile everything, and while you're at it, you can just add the dno heartbeat flag, so you can disable the heartbeat stuff completely. I don't really know if it's practically relevant for TLS over TCP. It doesn't really make any sense to have an additional heartbeat protocol. It's just redundant. If you use Google's ModSpeedy on Apache 2, there is a beta package there which hasn't been updated for a while, I think a pretty long while. You should just remove it, because that's something that cost me the better part of Tuesday morning. ModSpeedy brings their own ModSSL for Apache, and that ModSSL is statically linked, or there's a statically built copy of OpenSSL in there, and that's a vulnerable static copy of OpenSSL. And what ModSpeedy does is basically it changes the load statement in your Apache config to load that new ModSSL. And if you do a2dismod to disable the module, as I did, you don't actually change that load line. So the module is disabled, but it's still loading the wrong ModSSL. And that was really hard to debug because I just didn't have that ModSpeedy stuff on my screen anymore. So you should probably remove that. I talked to a Google guy yesterday, and he said he might look at what happened there and might look at if an updated version could be pushed out. So the really important question is, what about our certificates? I think I have about 180 SSL certificates deployed from our customers, and it's possible that their private keys have leaked. We know of a proof of concept scenario, which is very limited right now, but might expand in the future, where you can have a freshly restarted Apache on FreeBSD, and if you do the heartbleed check on the first request, you will see the private key for the SSL certificate that answers the request. So it's not impossible. It's probably very hard at the moment, and it's not deterministically possible to dump the private keys, but it's possible. So if you go by the book, you will have to revoke and reissue your certificates, your most important or most widely deployed certificates, if none else. So basically, if you have wildcard certificates on 20, 30 machines, you will probably have to revoke them. And you will have not only to reissue them, but you will have to revoke them, because if someone got your private keys and they also have your certificate, obviously, because that's public information, they will be able to man in the middle. They basically have a valid certificate with your domain on it, and they can sign or do whatever with it as long as it's valid, which is going to be probably a couple more months. So not only do you need to reissue, you actually need to revoke your certificate. Some CAs offer free service, but that's usually only reissue, and I don't think that really fixes the problem. You will have to try to get your certificate revoked free of charge, and good luck with that. If you don't have perfect forward security in your, or perfect forward secrecy in your web server's crypto algorithms, you might have an additional problem, because whoever sat on your line and sniffed your SSL traffic is now potentially able to decrypt it. But that's probably a little bit far-fetched. I don't think this is an APT attack or NSA is behind this or something. It's just an honest program mistake, I guess. And I guess the guy who did it is probably very, very embarrassed right now. So that's for our little interruption. And now back to our regular scheduled program. I was actually going to talk about what we call, or what the industry calls, software-defined networking, basically what you can do with Open vSwitch. And that's what we're going to look at for a little while. Basically, first a high-level approach. So what is SDN? Let's get little buzzwords out of the way. And what are we going to do, or what were we going to do with this stuff? And then I'll have an introduction for Open vSwitch and tell you how we deployed it, which is probably not the best practice, but this worked for us. Then differentiation between front network, back network, public network, firewalling, and then trying to tie it all a little bit together. So what are we talking about here? Software-defined networking is something that's been circulating for, I don't know, 2 or 3 years now as a buzzword. And it's being very heavily hyped with competing standards at the moment. And I don't really like those hype buzzwords, because normally they are just hiding something that we have been using for years, and they just give a little shiny package around it. What we do here is basically we decouple the actual networking decisions from the bare metal that has the networking ports. Essentially, we kind of virtualize parts of our network, and we try to separate or decouple our control plane, our data plane. So whatever does the switching doesn't decide where to send data or where not to send data. That's decided somewhere else. We have a couple or very many vendors that jumped on this train. Of course, all the big networking vendors, also VMware, OpenStack, the virtualization middleware vendors are also deeply involved here. One of the main keywords for OpenFlow, and this is where I will very closely watch for you, Frown, is OpenFlow, which introduces the concept of imperative control. Basically, it says that whatever does the switching is dumb, doesn't have its own logic or intelligence. It just has the ability to read and interpret a decision that has been made by someone else, and that's the OpenFlow controller. Basically, the first packet of each flow, which is a tuple of ports and IP addresses or MAC addresses, stuff like that, is sent through the controller, which applies a set of rules given to him and then makes a decision. And every subsequent packet of that flow goes directly through the switch, because the switch also already knows which rule to apply, has these cached, and can forward directly. There's also a new concept which was introduced rather recently, I think a couple of weeks ago, which is called OpFlex. It's an initiative by Cisco, who probably feel a little bit threatened by the idea that switching hardware should become very, very dumb again, because then they cannot sell expensive smart switching hardware anymore. So it's kind of their answer to OpenFlow. And there are a couple of other vendors already on board. Citrix, for example, Microsoft, Red Hat, Canonical. And there are some not on board. The Big J, for example, HP has been left out, Huawei, so they will have to copy from Cisco firmwares, I guess. And VMware is also not collaborating on this standard. The idea behind OpFlex would be that you do not do what is called imperative control, but declarative control. Basically, there's a high-level declaration of how the controller wants traffic to flow, and the switch, the forwarding plane, the data plane, actually interprets that high-level rule into flow-based rules that are then interpreted by the forwarding plane. It's a proposed standard for IETF, which is downloadable via the usual channels. And of course, the altruistic goal that's being propagated is we want to eliminate a potential single point of failure. Right now, in these imperative setups, the controller is a single point of failure for the whole networking. If a controller controls maybe a dozen or 100 switches, and the controller fails, it's, I don't know, an electricity problem or something like that, all the switches cannot continue switching as soon as the current flows are ended, so no new flows can be accepted and forwarded. And Cisco is saying that we can eliminate that single point of failure by just putting more logic into the switches so they can forward even with their controller not being available anymore. And the egoistic goal for a big networking vendor is, of course, to sell smarter switches, which are potentially more expensive because they have more complex software built in and potentially stronger hardware to actually make the switching decisions. The open source contender or product for this is Open vSwitch, which is maintained on openvswitch.org. Current stable release is 2.1 something, and long-term release is 1.9. So they have an LTS concept, and they you can basically deploy a long-term service version, which we do. It's open sourced, dually licensed under an Apache license and GPL. The Apache's part is the controller, and the GPL part is the kernel module that does the data path. So because it's part of the kernel, it has to be GPL. But the controller is under a non-viral license. It's a multi-layer switch, which can switch on layer 2s and 3, for example, and it supports a lot of interesting features, of which I'm not using, I don't know, a fourth or something. We're probably not using 1/10 of the potential of Open vSwitch in our setup, and I guess it has something for everyone. So it supports VLANs, of course, but also supports NetFlow and SFlow for traffic accounting. You can do LACP like you would with any regular switch, and you can also do filtering on layer 2 and 3. So high-level overview would be you have a kernel module in the bottom that sits in the kernel and does the actual forwarding, and you have a vSwitch daemon and a OVSDB server which sit in the user space and contain the OpenFlow and interpret the OpenFlow rules and forward interpreted rules to the kernel module to actually do the switching. And you can have an external that's very tiny up there, but it says off box, the top dashed line. You can have an external control cluster which basically does all the decisions externally and manages a whole spread network. In the middle sits the OVSDB, which is basically a database for switch configuration items. It contains the definitions for the bridges, tunnels, interfaces that run on your Open vSwitch instance, and it contains also the addresses for the controllers if you have external controllers. Configuration is, of course, reboot safe, so you wouldn't have to feed the whole configuration into the database again after rebooting. It's not anything we know, as far as I know. So it's not MySQL, SQLite, Mongo, or something like that. It's a custom database format, speaks a custom protocol, and it's basically log-based. So you can see all the changes by dumping a log of the database, and that's very good for change management or for debugging. If you see something has changed and now it's not working anymore, you can basically see all the changes and then roll back to the last working state. As I said, OVS does imperative control. So basically all intelligence is in the controllers, and the data path component which sits in the kernel only carries out instructions. It's a kernel module licensed under GPL v2, and the controller lives in userland as licensed under Apache 2.0 license. So graphically, this looks like this. The concept is that everything is a flow, so a combination of input and output ports, TCP or switch ports, VLAN, MAC addresses, IP addresses, TCP and UDP ports on layer 3 can define a flow. And the more defined a flow, the smaller it usually is, or the less packages it has, and the less ports or forwarding decisions it would match. The controller basically, on the first packet sent for each flow, the packet is forwarded from the data path to the controller, which makes a decision how to deal with that packet and the subsequent flow, and forwards that decision back down to the kernel module, and every subsequent packet is in a flow is sent directly through the data path. So flow interpretation is only performed on the first packet of each flow, so you would have to, or you would want to make flows as large as possible so you don't have that much interpretation work. The kernel module has a cache where basically there's a hash table of flow IDs to forwarding decisions, so it doesn't even have to look up the decisions anywhere else. It just can use cache decisions and is therefore rather fast. There's a set of command line tools which we use for managing our setups. I guess there's many smarter ways to do that, but that's how it worked for us, and we tend to never change the running system. There's OVS VSCTL, vSwitch control for switch management, OFCTL for flow management, where you can basically modify or flow rules, and there is a database management tool which is called OVSDB tool, which you can use to dump your logs or check flow debugging and stuff like that. So our angle here is, of course, we are a hoster, and it was our goal to host a public cloud. So we wanted to have an IaaS product offering that, based on open source software, can be used by customers to host VMs with a couple of features. And first of all, the VMs would need networking. So you can probably see where this goes. This is a very tailor-made solution that we made for our purposes. It's just not a general purpose solution. It works for us, and it might very well not work for you. It might also work for you too. You will have to see for yourself. What we wanted, what our requirements were, was we wanted, of course, an internet-facing frontnet interface for every VM, so they can get a public IP address and they can talk to the internet. We also wanted them to have a back-end network that is only shared with other VMs of the same customer. So basically, we wanted VLANs for VMs. We wanted the VMs, of course, to be isolated in the network. We don't want other customers to see traffic of their neighbors on the same machine, but I guess that's a given. We wanted firewalling, off-VM firewalling, that is, so people could have a packet filter that sits in front of their VMs and not on the VMs. We wanted to be able to shape, mostly for terms of service breaches. So if someone has an owned machine and is just shelling out spam or traffic, DDoS traffic, we wanted to be able to put them back to, I don't know, 1 Mbit or something like that. We wanted some rather fine-grained accounting to do IP traffic accounting, and we wanted to be able to live migrate from one host to another. So in an implementation, it would like this. You have your VM boxes, which are the orange boxes, and a lot of VMs sit in them, and basically the physical boxes are connected to a front-end switch and to a back-end switch, and the VMs will have to get their networking from there somehow. Virtually, it would like this. There are 2 interfaces in each VM. One of them, the green one, goes up to the internet and goes through a firewall, and the red one basically only goes into other VMs of the same customer, but can span across multiple hosts. So we would have to have inter-host VLANs, and it's basically not possible to go from there to the internet, only to other VMs that belong to the same customer. In the stack, it would look like this. Of course, everything is basically connected to Open vSwitch via a bridge. The Open vSwitch instances are connected to each other, and they also have a internet-facing interface that goes outside. So how to do this? We turned out to be compiling Open vSwitch ourselves. There are packages in apt for, I think, Ubuntu and Debian. I'm not sure which versions they run because we don't use them. Do you know about that? Okay.
But if you take plain Ubuntu LTS 12.4, you will have to also install the new kernel modules because it's a very old one. It doesn't work.
So it's probably a fair bet to compile stuff yourself, I guess. Yeah.
Why don't you use the 1.4.2 from Debian? So if you want APT, I think you run Ubuntu or Debian.
We run Ubuntu mainly.
Okay, so in Debian we run a vSwitch with 1.4.2. It's 1.4.2.1. We are pretty happy.
The question was why we don't run the Debian stock packages, which have Open vSwitch 1.4.2, you said. I'm actually not the guy who admins the machines, but with older Open vSwitch versions, we had issues. I don't know the exact issues, but there were issues, and eventually we landed on 1.9.3, which is the current long-term stable release, and we're pretty happy with it. We don't need any of the newer features right at the moment, and we tried newer versions, and they don't really work with our farm. So it's after you have a dozen or so hosts, it becomes a little delicate to switch to new Open vSwitch version because you just introduce downtime for pretty much everyone. And mixed setup proved to be not a really good idea. So having different Open vSwitch versions talk to each other, that's not really 100% super stable. So we basically settled for the LTS release, and we're pretty happy with that. But whatever floats your boat, if it works for you, it's fine. Yeah, I think everybody compiled something before, so I don't think I should probably talk about this. There's a kernel module, and it can be enabled. I think it's in mainline, or isn't it? From 3.3 plus. You can just enable it, recompile, and then mod probe. After that, you would have to create the Open vSwitch DB. There's a schema file, which is, oh sorry, there's a slash missing there. There's a schema file which is in the source code for Open vSwitch, and you would usually, we usually do that. You can probably discuss this very long. We usually put our Open vSwitch stuff in user local, and the database would sit in user local etc Open vSwitch then. And one thing that proved to be important for us is that Open vSwitch and the OVS database need to be started before the actual networking starts, and that kind of conflicts with how Ubuntu and Debian run things. So you would probably have to remove the networking startup scripts from your RCD and put them into RC local, and put the OVS vSwitchD and OVSDB server calls before them. So you can be sure that your Open vSwitch environment is running before you set up the rest of the networks. Then initially we start bridging. Basically we do a lot of bridging, and we do a lot of tapping. First off, the examples would be we have a frontnet VLAN, basically broadcast domain for maybe 100 VMs at a time or something, and the VLAN ID would be 199. So basically we tell Open vSwitch to add a bridge on VMBR1, and we tag it with VLAN 199. And then we log into our machine via some kind of out-of-band control, IPMI or something like that, because we're going to lose networking. So we add the port to add our Ethernet port to the bridge, and we see the machine drop from the net because it has the wrong VLAN tag on the main Ethernet port now. So we then go to our switches and make the VLAN known to the physical switching port, so the machine comes back online. For VMs, we use tap interfaces, like probably most people do. We run KVM QEMU, so you see a QEMU call here for starting the machine. And basically what we do first is we add a tap device and own that to the user who runs our middleware scripts. And then we start up the QEMU instance. We give it a custom MAC address, which is here. And we bind it to the tap interface that we have here. That would probably have to be VLAN 199. I didn't modify the script correctly, sorry for that. After that, you can bring up the port, and you have a running tap interface now that runs or that connects to the VM, And now you will have to find out on which actual Open vSwitch port it runs. So basically, we want to see from the tap interface where the virtual cable connects to the virtual switch. We can do that with OpenFlow control. We can just show our main bridge, and we just grab for the tap device that we just connected. And now we can see the port number on the Open vSwitch instance, and we can use this port now for managing our flows. If you want to have multiple interfaces per customer, basically you just assign more tap interfaces and you assign different VLANs. If you want to have one VLAN per customer, you'll run into problems after you have about 4K customers. If you have them on the same node and you don't have to make the VLANs publicly known, you will probably not have an issue, but usually you will have to have cross-node VLANs because you cannot deterministically say which VM runs on which node. At least we don't run VMs of one customer on one node. Doesn't make a lot of sense for HA purposes. If you have to have inter-node private VLANs, you will have to do whatever you do to make VLANs known on your physical switches. And then you'll have cross-node internal networking, which proves to be very helpful for customers. But of course, usual VLAN limits apply. So something that Yves will probably talk about are overlay networks. He's going to have his talk at 4 o'clock, I think, 5 o'clock. He's going to talk in depth about OpenStack networking, and is probably going to refer also to the rescue here, which would be overlay networks, stuff like VXLAN or something, which we currently don't use because it's not present in our Open vSwitch version. Open vSwitch 1.9.3 doesn't have VXLAN. I think that's a 1.11 plus or something feature, or relatively recent. So we are not currently able to use that, but we probably will have to evaluate it pretty soon. So now we have an interface which is connected to virtual switch port, and that port number was 1820. We can see it up there in the first line, and now we can start filtering stuff. So first thing we would probably want to filter is MAC and ARP spoofing, which we can do with OpenFlow. So basically what we do is now we add a bunch of flows which concern the port that we defined here as a variable. It's up here, 1820, so this is the port that we just brought up. And this resubmit is probably even redundant, so it's not really optimized for performance. You can probably do a lot of performance optimization on OpenFlow rules. But basically what we do is we check for the MAC address and the MAC source. And if it doesn't really fit, we just drop it. Rules are interpreted numerically descending. I never seem to memorize that. Numerically descending is right? Yeah. We of course know the MAC address because we control the hypervisor, and we can just define a MAC address to be present in the VM. And also we of course know the IP address because it's the IP address assigned to our VM, so we can bind these two together and prevent bad guys or bad customers from spoofing there. That would be ARP spoofing, I think, or maybe I just copied the wrong slide. There's a couple of caveats for that. Sometimes you actually want customers to be able to spoof, because that's one of the features that you would use for stuff like ZRMon or other Linux HA solutions to hand over the virtual IP addresses. And we have a couple of customers who run HA clusters across our cloud cluster, and they have VMs that sit on n different nodes, and each VM sits on a different node than its counterparts. And these people have to be able to bind a second IP address to the MAC address. And if you want to cater for this by design, you can just assign sequential MAC addresses to VMs from the same customer. So you can have a per customer MAC address pool, and you can assign them sequentially. Then you can use wildcarding in the OpenFlow rules to actually apply the correct filters. Or you just have to set additional rules to cater for the cluster or virtual IP address, however you want to call it. You should probably never allow customers to enter their own rules anywhere, but I think that's a given. So this is another, now we're moving a TCP to TCP, so we're moving a layer higher This is another OpenFlow example where you can see that we are now actually doing packet filtering. So we have a rule that defines traffic between 192, 168, 1, 123, and 12, 13. And the destination port would be 18, HTTP, and we don't want anything to happen there, so we drop traffic. It's a very specific, very straightforward, very simple rule, which effectively blocks traffic to port 80. You can also use port ranges here. That's a slightly more complex thing here. The port range would be here. These are hexadecimal bit masks. So basically, what you do to calculate the port mask is you use like sitter masks only for ports. And what we do here is we drop traffic from ports 1512 to 1516. From Open vSwitch 1.11, there's wildcarding for pretty much everything. You can wildcard MAC addresses, you can wildcard TCP, UDP ports, and I think this concept is called mega flows because you do what I said initially, you drastically increase the matches for your flow setup. So basically, what we see here is a definition for one flow, and it concerns traffic between a /24 network and a /32 IP address on 4 different flows. So the data plane, if it sees traffic come to one of these ports, only has to cache one flow rule, not 4 of them, or 256 for the whole /24 network. It's just one flow, it's one rule, and one cached entry, and that makes everything, of course, a lot less memory dependent, and for large networks, it would probably scale really, really well. But of course, you broaden your matches, which is not a problem for a drop if you want a lot of security anyway, but might be a problem for permissive rules. And regarding permissive rules, this is our fall-through rule, which we have at the end of each flow definition or firewall definition, and that basically accepts everything that's not matched by previous rules. So this looks, just a very quick look at this in production. I have the configuration for my own VM here, and yeah, that's just the rule set that we apply here. So this is my public-facing IP address. And well, nothing really fancy here. It's basically what I have on the slides. And we also have I think we have a fallback to IP tables if the Open vSwitch module can't be found. But this is what we use for Open vSwitch. So nothing really surprising here. Okay, on to the other features. We do accounting very simply. We just use the interface counters on the tab interfaces, and we grab the counters regularly and just put the deltas into a database. With Open vSwitch, you can also use NetFlow or SFlow, and I guess your mileage will vary about how well you can do that for actual accounting that flows back into billing. Especially for NetFlow, you will probably have really a lot of data, and you will have to have a strong box interpreting that. But that goes for every NetFlow setup. So we didn't go there yet. If anyone here does NetFlow or SFlow for accounting Open vSwitch, I'll be glad to hear your experience. Nobody? Okay. Next feature would be shaping. That's a topic where, especially in the low-cost area, where you have a VM that's basically $5 a month, you don't want that VM to shell out 20 terabytes of traffic. So you need a way to somehow polish this. Simply put, you can basically go ahead and just do ingress polishing, and you can just limit the overall data rate. So basically you can say this is now a 10 Mbit interface, not a gig-E interface anymore, which is very close to the Linux shaping syntax. You have a normal flow rate and you have a burst rate, which goes on top of the flow rate, so these are additive. You can also have very complex QoS, which basically does Linux HTB, and you can configure very, very fine-grained how you want to apply quality of service parameters to your cloud. Again, we don't do that. We do shaping occasionally for customers that fall out of the fair use policy, but and that works mostly as intended. But we don't do any complex QoS. So if anyone does that, does OpenStack networking support that out of the box? Is there ways to do that in OpenStack?
It depends on the plugin you use.
Okay.
But the normal plugins we have at the moment.
Okay. Good. So shaping for just bandwidth shaping is rather simple. Complex stuff can also be done, and you can basically do QoS on, I don't know, port 80, or you can shape BitTorrent traffic or whatever you want, and that's also supported by OVS. It's a bit tricky, I've read, but it's possible. Regarding live migration, OVS has support for live migration by establishing a GRE tunnel between the OVS instances on the receiving and the losing host. What we basically do is we start the VM up in suspend to RAM mode on the receiving host and stop the VM on the losing host down the interface and then bring it up again. And we have rather short uptime also that works. There are live migration mechanisms in OVS. Again, we don't really use them. So if anyone has experience, I'm just looking at OpenStack again. I'd be happy to hear. We do a lot of things until we find a working solution, and then we tend to stop looking at them, because as soon as it works in production, it's probably fair enough to continue using it. And we are very sensitive about our uptime, so it's out of the question to update to a new OVS version just to have this and that feature. That's not really in the picture for us at the moment. So the layer 2 based live migration mechanisms that exist in OVS, I don't really have a clue about them. So there's a couple of very good presentations about, among others, these features, which are in the link collection at the end of the slide. So if you want to clue yourself up, either you can look at that or you can look at Eve's session at 5 p.m. So that concludes everything. I think we're just on time here. Thanks, everyone. I hope you learned something, or you could just laugh to yourselves on my expense. And if not, well, I would buy you a beer, but it's 10:25 a.m., so that's maybe a little early. But if you have any more questions, just feel free to shoot now. Yeah.
You talked about the single point of failure in the controller.
Yeah.
How big is this problem?
That's a good question. We don't have the problem because our layout is different. Just repeating the question, I was asked how big the single point of failure problem for failing Open vSwitch controllers is. We basically co-locate the controller on the machine that runs the Open vSwitch instance. So there's not a lot of failure scenarios. The process could crash because of out of memory or because of reasons. Then you would have to restart networking pretty soon, or you will lose connectivity on the instances. Yeah.
Does it mean that each virtual machine host runs its own controller, and you don't have any system-wide host over kind of?
Currently, we don't. No, we have a centralized host that does the management, but it's basically configuration management. So we don't use I said that earlier. We don't use the OVS internal controller mechanisms to have basically one central controller, that central Open vSwitch controller. We have a central machine that basically manages the configurations, and we currently manage everything by configuration file and not with a central controller. So we don't have that failure scenario, but that wasn't intentional. Honestly, we just felt it to fit into our workflows better and to our deployment workflows better. And if you have a central controller sitting in the middle, and that controller fails for some reason, you will have to restart it rather quickly, because otherwise, as soon as the currently cached flows are not valid anymore, so new traffic comes in with a different flow spec, you will not be able to accept that. I think there's a fail open mechanism in Open vSwitch that can be used for that, where you basically forward everything, but well, that's also not the best solution. And there's also, I think, a possibility to cluster these controllers so you can have high availability to avoid for those pitfalls. Yeah.
So the management solution which controls which data configuration of the individual hosts. So it's custom built. It's nothing based on.
I'm sorry, I didn't hear you.
KMO and configure the switch with your custom solution.
Yeah, exactly. The question was if we have some stock solution or something custom built, and we have a custom solution that we wrote to manage the configuration stuff. It's not Puppet or something. No. Okay. Any more questions? Yeah, in the corner.
And do you happen to know if it's possible at all to spread out the controller part of Open vSwitch, or if it has to be a single machine?
As far as I know, you can cluster it somehow. It doesn't have to be a single machine. Correct me if I'm wrong. It doesn't have to be a single machine, and you would be able to spread it out. But for example, have an HA solution to avoid single point of failure. Should not be an issue. We don't use this, so I don't have a lot of mileage here. Okay. You will receive the slides after the conference, I think. And in case you want to have a look, these are the presentations I was talking about. And I wish you all a nice rest of the conference, and thanks for listening.